Okay, some announcements before we start. We'll have the exam is Tuesday night at 7 p.m. in this building. I think it's 166. It's right over there, right in the lobby. I'll give you the exact, confirm that. But anyway, so it's in 7 p.m. Tuesday night in this building. Monday from noon to 3. There, and this will all be on announcements. But Monday from noon to 3. There'll be just a study session with myself, and hopefully the TAs can be there too. ECA 225, that's Monday from 12 to 3. Open study session. There'll be some review materials I'll post on Canvas. You can work through that. You can work through online homework, written homework, look at old exams, all that stuff. So Monday, 12 to 3, ECA 225. Come and go as you please. You can come at 1 and leave at 2:30. Anything you want. The more studying you do before you come, the better. All right. So then it's when you dig in and you work hard, and then you have conversations with myself and other students. That's how you learn the most. So study as much as you can this weekend before you come to that. If you start your studying at that review session, that will be less beneficial. But you could still come. Questions on that? So then in terms of homework, we're going to have one more written homework due Friday based on today's stuff, and then there's one more online homework. We'll make it due Monday after that, like I said, like Monday at 5 p.m. or something. Okay, so one more written homework for Friday, online homework for Monday at 5. Do you have a question?
Yeah, so if we're unable to take the exams earlier, or is it like we have to?
You have to take it at 7. That was... Okay, other questions about scheduling, logistics, all that stuff? Okay, so we're talking about polar coordinates. We said, and you guys worked on some polar coordinates and recitation yesterday, and we're seeing this as a whole completely different way of plotting points and graphs and functions in a plane. What? Because it's based on an angle measure, right? Angle measure and distance from the pole. So it's based on angle measure. And that's our standard trig angle, swept counterclockwise from the horizontal axis. And then distance from the pole. So what is this point right here? So we want to graph this point right here. So that means what? How much and what comes first? The angle or the R value? Angle comes first. And what's the angle? 5 pi over 6? -1. All right, so the angle is -1. That means I'm going to go, and what is 1 radian? Negative means clockwise, and what is 1 radian? How far would I sweep? But what does it mean? What does 1 radian represent? It's going to cut an arc length, right? It's all about arc length, right? 1 radian is an arc length of 1 radius, right? 1 radius. That's going to put me right about here. That's that's -1 radian, right? So this is my angle measure right now is -1 radian. And then once we have established the direction of positive r, so the angle gives us the direction of positive r. And then once we've established that direction of positive r, we're going to go that many units along that direction from the pole. So 5 pi over 6 is about 3. It's pretty close to 3. So we're going to march out here, and somewhere around here, somewhere around 3. My r is 5 pi over 6. I don't know, is it less than 3? Probably less than 3. little bit less than 3. Okay? So this is our way of plotting points in polar coordinates. Okay, so then we start talking about sketching graphs. So sketching graphs of polar functions. So polar functions are of the form r is a function of theta. So polar curves r is a function of theta. So last time we did r equals 2 sine theta. And we said, what was the key to sketching this graph? What's the key? Or the method that we want to help us really understand these polar graphs? Well, it's about sketching this function in rectangular coordinates first, x and y, where r is on our vertical axis. Well, not x and y, but r is vertical axis, theta is horizontal axis. And so we sketched that function in lecture last time. And we use that graph to help us sketch the graph of the polar graph, right? So we said, what? As theta goes from 0 to pi over 2, r does what? 0 to 2. So as theta goes from 0 to pi over 2, r goes from 0 to 2. And as theta goes from pi over 2 to pi, r goes from 2 back to 0, etc. Pi to 3 pi over 2, theta goes from 0 to negative 2, right? And so we have to be really confident about what negative r values mean for values of theta in order to do this, because it's like dynamic, right? The angle is changing, and so we got to be really confident about how negative r values work. And then from 3 pi over 2 to 2 pi, r goes from negative 2 back to 0. And so let's put that in. Two sine theta. We're going to start at 0. I put it in the wrong place. This one. There we go. Okay. Okay, so we're going to go from watch it happen. As theta goes from 0 to pi over 2, r goes from 0 to 2. Do you see how r increases? Watch that point. That point, r is getting greater and greater and greater as the angle increases from 0 to pi over 2. And we saw that sketched out that curve, right? That's r increasing from 0 to 2 as theta increases from 0 to pi over 2. And then what happened next? As we go from pi over 2 to pi, that's the second quadrant, r goes back down from 2 to 0. So keep your eyes on the point, right? Eyes on the point as it decreases from 0 to 2. Simultaneously, the angle increasing from pi over 2 to 3 pi over 2. Okay, so now in the third quadrant, we're going to sweep from pi to 3 pi over 2 like this. And r is going to go from 0 to negative 2. What would that mean? What quadrant would that be in? If we're pointing down here in the third quadrant, negative r values point which way? Up in the first quadrant, right? In the opposite direction. So here's r going from 0 to negative 2 as the angle goes from pi to 3 pi over 2. That just retraced that first part of the curve we already had, right? So that retraced it. And similarly here, as you go from 3 pi over 2 to 2 pi, we come back from negative 2, watch the point, from negative 2 back down to 0. So what is the period of this curve? What's its period? Meaning what range of theta gives one full cycle? No, this right here. It's 2 pi. But the polar graph, in polar coordinates, what's the period? Pi, right? So pi gives us the full curve, and then it starts over again. So in polar coordinates, for the polar graph, the period is pi. So it was often, so what happens? Sometimes the period of the rectangular graph and the polar graph are the same. Sometimes they're different. It's just each one is different. This isn't going to happen every time like this. But this is an example of how what it takes to sketch the polar graph may be different than the period of the rectangular graph, or it may be the same. Okay, so that's where we left off, and we asked the question, is it a circle? So we want to show mathematically whether or not it's a circle. So it looks like a circle, but just because it looks like a circle that's not mathematical justification. Okay? Maybe it's slightly egg-shaped. Okay? Who knows? All right, so what do we look at? We look at our equation, r equals 2 sine theta. That's what's going to be the key to determining if it is a circle. So what can we do with this? We know the equations of circles in rectangular coordinates. So if we could change this into rectangular coordinates and get the equation of a circle, then that would confirm it. So we need to transform this into x and y. And what was our means of transforming to x and y? What does x equal? R cosine theta, right? And y is, that's our right triangles, right? X and y coordinates make up the legs of a right triangle, where r is the hypotenuse for any given point. So I want to get this to look like x and y. So I have 2 sine theta. Well, what would I really want? R sine theta, right? So what can I do to this to make my life easy, right? If I had an r in there, yeah, so let's multiply by r, and that would just be then what? 2y, right? But if I multiply this side by r, yeah, now I've maintained the equality, multiply both sides by r, and this is really helpful because now I have r sine theta, which is, the right side is simply 2y, and the left side is Pythagorean theorem, right? X squared plus y squared. X and y are the legs, right? X and y coordinates. X, y are the legs of a right triangle whose hypotenuse length is r. So r squared is x squared plus y squared. And r sine theta is 2y. So, is this a circle? Well, remember back in your pre-calculus days, we need to complete the square. How do you complete the square? You take half of the linear coefficient and square it. So half of -2, -1, squared is 1. That will complete the trinomial perfect square. But if I add 1 on this side, got to add 1 on this side. So I got to complete the square. This is a blast from the past. Complete the square. If I add it to this side, I add it to this side. Now I've got that perfect square. So I got x squared plus y minus 1 quantity squared equals 1. And so now we can answer, is it a circle? Radius? Yes, circle. Radius equals 1. Center is 0, 1. Does that agree with what we're looking at, that blue curve? Center, so thinking about now back to the rectangular coordinates superimposed on this, 0, 1 would be right here. Radius 1. So this mathematically shows that that indeed is a circle, because this statement is mathematically equivalent to this one. All right, how about the function that's the circle centered? So if I want the circle centered at 0, 0 with radius 3, what would that be in polar coordinates as a polar function? So can you imagine that circle? So what would my polar function be for this circle centered at the pole with radius 3? What would the polar function be? Polar functions are, r is a function of theta, right? So what function of theta would give me the circle radius 3 centered at the pole? R equals what? Look, for any theta value, what's my value of r? 3. Therefore, 3. It's just r equals 3. It doesn't matter what theta is. You always want r to be 3. 3, a distance of 3 away from the pole for every theta. So that's a constant function in polar coordinates. That's a constant function. Constant functions give us circles centered at the pole. Constant functions give us circles centered at the pole. So the point here is that polar coordinates are very conducive or compatible with circles. Okay? What about lines? What about lines? How about, so we're familiar with lines like in y equals mx plus b. So let's just pick a line here. Y equals negative 2x plus 3. Is that compatible to xy coordinates, rectangular coordinates? Very, right? What is negative 2? That's our rate of change. Given any change of x, what y changes by? Negative 2 times your change in x, right? So, we know that forms our slope, and so that's very compatible. What about in polar coordinates? What is y? Let's switch this to a polar function. Y equals r sine theta. X equals. So in polar coordinates, this equation would look like this. And what do we want? We want r as a function of theta. That means we want to isolate r. We want to isolate r by itself. So I'm going to move all my r terms over to the left. If I want to isolate r, what do I do next? Factor out r. Last step. So here is my r as a function of theta. R equals 3 divided by sine theta plus 2 cosine theta. What about that function? Straightforward, simple, user-friendly, or kind of complex and weird?
Not as nice as the
Right.
Cartesian one.
Certainly, this is more straightforward, user-friendly. This is more convoluted, right? More complex. It's got 3 over sine theta plus 2 cosine theta in the denominator, right? So that's not straightforward. But if I come up here and I graph that, so I'm going to come up here and graph 3 divided by sine theta plus 2 cosine theta. What happened? Why doesn't it still graph function g? That's really weird. Oh, there it is. So that's our line that we're much more familiar as negative 2x plus 3. Here's my y-intercept of 3 with a rate of change of negative 2. But I graph that as this polar function that we found when we did the math. So it can be done, but it's not well suited, right? Lines that are based on a rate of change of y with respect to x are not well suited or compatible with polar coordinates, and therefore the equation of that line is a little more different, a little more complex, right? Because it's not a nice suitable match the way that this equation would be for rectangular coordinates. Yeah.
Are there going to be any values of theta for which sine theta plus 2 cosine theta is equal to 0? zero,
Ye-
so you would end up with a gap in the line.
Yeah, exactly, right? So that's another thing about this that's weird, right? Or that's, not nice. If there were values of theta that made the denominator 0, then you'd have then,
Yeah.
let's see. Yeah, then you'd have r would be undefined. So I think what happens is that's that's like kind of an asymptote, right? So there's angles of theta that are, I think that's maybe, yeah, that's the angle of theta that's parallel to this line. So it's kind of like that. That's kind of like the asymptote of this.
Oh,
So that's what you'll get. You'll get the theta angle that runs parallel. So there's no r value that will give you a point on that line. Yeah. Okay. So this idea of switching back and forth between a polar graph and a Cartesian graph is important. And so I did a couple examples of that, changing the sine 2 theta into the equation of the circle, changing the equation of the line into the polar version of that same line. Any questions on doing that? Okay, well, we need more practice sketching these polar graphs because these can get hard, but they're real good exercises and understanding polar coordinates. So the next one we're going to try is 3 sine theta plus 1. So as I'm getting my screen ready, what are you going to do first? We're going to sketch 3 sine theta plus 1 in rectangular coordinates. 3 sine theta plus 1. So you do that while I'm getting ready. Sketch 3 sine theta plus 1 in rectangular coordinates. If you brought your polar graph paper either from Lecture Monday or recitation, then you can use that. I do have a few extra blank sheets if you don't have any polar axes. 3 cosine theta plus 1, you're sketching that in rectangular coordinates. 3 cosine theta plus 1. Just people raise their hand. Okay, where's Jennifer Lee? Jennifer Lee. Is Jennifer here? Yeah. So what I'd like to know is, so these cosine and sine waves, they have a max, a midline, and a min. What's the min and the midline and the max of this graph? Good, okay. The min is what? -4? So the max is 4, I agree with that. What's the min? So -2, right? So the max is 4, the min is -2, and what's the midline? 1, right? 1. Okay, and so we got our max is at 1, or sorry, max is at 4, midline's at 1, min's at -2, and then where does cosine start? At the max, the midline, or the min? At theta equals 0. The max. All right, and we're gonna break up at our midline. We're gonna break it up into 4. 4 intervals, right? 4 equal intervals. That's kind of what these sine and cosines are most easily broken up into 4 intervals. And we're going to start at, and that's the first interval is at what? We know that's pi over 2, pi, 3 pi over 2, 2 pi. Okay, and so then we're going to start at the max, and as you go from 0 to pi over 2, we go from the max to midline, which is 1. Okay, and then as you go from pi over 2 to pi, we go from the midline to the min. And what happens in between there? So we're going to note that what happens right there, the r value is positive, but then it's 0, and then changes to negative. So that's going to be a key for drawing our graph. Okay, then from pi to 3 pi over 2, from the min to, not straight. Okay, and then from 3 pi over 2 back to 2 pi, back to the max. So this is something like what we've got, right? And then here along the midline is where it intersects at those key breakpoints, pi over 2 pi, 3 pi over 2, 2 pi. Okay, so now we're ready to sketch the polar graph. And this is where we want to use the polar graph paper, of course. And so, as we go from, as we go from 0 to pi over 2, r goes from what to what? 1 to 4, is that right? 4 to 1, right? So r goes from 4 to 1, right? So as we go from 0 to pi over 2, we go from 4 to 1. What will that look like? So we'll start here at 0 at 2, 3, 4. And so we can see that point right there. There's the point. And then by the time as we sweep from to pi over 2, that r is going to decrease down to 1. So here's the big mistake that students make. They do this. They go like this. Well, I know it starts there at 4 and ends there at 1, and so they go like this. So what's happening there at the end? Is r decreasing there at the end like that, if you draw it that way? No. So think about as it's changing, you get little decreases in r the whole way. So for each, I'm not plotting points, I'm just kind of giving the idea that r as this arm lifts up, right, as the angle increases, you just think about the r decreasing down that terminal side. So let's watch it. Ready? It's not a straight line. You don't plot points and connect the dots. So watch, ready? Watch what the point does. It decreases. See, it's still almost 4 there, right? It's still almost 4. Now it's decreasing slowly. And then it gets to 1. Look at all the decrease happens kind of at the end. See that? So it starts at 4, slowly decreases, then quickly decreases to 1. And that's by the shape of this graph, right? Up here, it's hovering around 4, so slowly decreases, then quickly decreases. One more time. Watch it. So slow decrease, then rapid decrease. By the time it gets to pi over 2, we're at 1. So that looks like this. Okay, now what happens so now this is harder now. From pi over 2 to pi, what does our r do? From pi over 2 to pi, r goes from 1 to -2. But along the way, it goes through 0. And does it go through 0 closer to pi over 2 or closer to pi? Closer to pi over 2. So for just a little more angle here, our r value is going to head to 0. And then after that, where is r going to be? Where are we going to plot r after that? Which quadrant? So let's turn this off. So watch, for a little bit more angle, that r value shoots to 0. Watch the point. See that? Shoots to 0 right there. And now for these angles here up to pi, where is it going to plot? Fourth quadrants, right? In the opposite direction, negative r values. Here are my negative r values, the red axis. As theta increases down here, those are going to go there until we get to, what, -2. So watch it. So watch the point. R is increasing to pi. Maybe. Grabbing it, but I can't move. There we go. And then we're going to make it out to -2 by the time we get to pi. So this is the angle pi. right? Angle pi, -2. Watch it again. So it goes from 1 down to 0 and just a small interval of angle, and then for the rest of the way, it increases more negative, more negative, more negative, so you get to -2. Did you see it? Could you do it without the GC file? So let's watch it. Ready? Here, we'll watch it together. Turn it on. Watch. So down to 0, and then now negative, out to -2 by the time we get to pi. All right? Any questions? So you'll have to do this without technology, okay? There will be a no calculator part of the final. You'll have to do this. So you can't just say, oh, I'll just put it in my calculator and sketch the graph. No, this is really a great test and practice with polar coordinates, being able to graph these. So we're going to make you do it. Next from pi to 3 pi over 2, r goes from what to what? -2, back to 1, but along the way, through 0. Closer to pi or 3 pi over 2? Closer to 3 pi over 2 at the end, right? So it's going to, at the very end, it's going to cross through 0, the very end of this interval, and then head back to +1. So -2 to 0 to +1. So let's watch that happen. Here we go. So now that we've seen it, so it's kind of undoing what it did, right? So -2 back to 0 when it's almost to 3 pi over 2. And then out to 1 when it reaches 3 pi over 2. The last part is definitely easier. What does it do? It goes from what to what? 1 to 4 as the angle goes from 3 pi over 2 to 2 pi. So it's just gonna increase quickly at first, right? R is gonna head out fast at first, and then at the end it's just gonna slowly approach 4. So R increases quickly at first from 1, and then slowly at the end until it reaches R of 4 at theta equals 2 pi. So what's the period of this polar graph? It took 2 pi to graph the whole graph, which is the same as the period here. So sometimes they're the same, the period is the same, sometimes it's different. Questions on that example? All right, so let's let you take the wheel a little bit more here. Why don't you try R equals, so this is your homework, written homework for Friday, is practicing sketching these graphs. You have to practice doing it without technology so you're ready for the exam, okay? So we can't enforce that on the homework. We can enforce it on the exam though. That you're doing what I'm doing here, but when you're actually sketching it, you're thinking through. So let's do R equals 5 sine 2 theta. So what's our means of doing this? It's sketching in rectangular coordinates, R on the vertical axis versus theta on the horizontal axis. Make sure that's correct first. First, make sure you have that correct. And then you're using that graph to sketch the polar graph by looking at how R changes with theta. Okay, so no technology. Sketch this without technology. You're either making progress. Okay, maximum value is? Minimum? Right, there's no vertical shift, so it's -5 to 5. Period is? Right, so a value of pi is going to make this thing 2 pi, and that's going to take us all the way around in sine, right? So, but what we're going to find is that maybe we're going to actually need 2 cycles of it to get 1 cycle of this. Maybe, who knows? So now we're going to, Breaking it up into quarters means pi over 4, pi over 2, 3 pi over 4, etc. Sine starts at max, midline, or min? Midline. So go to the min or the max first? Max. Don't draw straight lines, right? These are curved like this. So there's our first cycle. Once we hit pi, we've hit a period. Something like that. Okay, now we're ready to sketch. Ready to sketch. So I'm actually gonna sketch it by hand here, and then we'll have GC make the pretty one. But I'll do it just because you have to. I'll do it too. So we say as what theta goes from 0 now to pi over 4, r goes from what to what? 0 to 5. So imagine this theta changing from 0 to pi over 4, and r is going to go from 0 to 5. So it's good to have kind of a place to shoot for. We're not plotting points and connecting dots, but it is good to have a target. All right, when we imagine as theta increases, that r is going to increase from 0 to 5, something like that. And then, as theta goes from pi over 4 to pi over 2, r goes from 5 back to 0. All right, now, as we go from pi over 2 to pi, r goes from 0 to negative 5. So let me just show the angle measure there. Showing the angle measure. As you go from pi over 2 to 3 pi over 4, where are we going to be focusing on? The negative r territory. We're going to go from 0 to negative 5. So where is 0 to negative 5 for this range of angles right here? Fourth quadrant. So what it's going to look like. So have a target point here. Our target's right here. But we imagine, so r going from 0 to negative 5. But our angles are up here, right? Pi over 2 to 3 pi over 4. R increasing negative from 0 to negative 5. And then from 3 pi over 4 to pi, back to 0. Then from pi to 5 pi over 4, from pi to 5 pi over 4, those are these angles here. Watch, ready? Here's pi to 5 pi over 4. We go from what to what? 0 to 5. So from there, from pi to 5 pi over 4, we're going to go from 0 to 5. And then back down to 0. Back to 0. And then finally, from 3 pi over 2 to 7 pi over 4, we're going to go from, so imagine where those positive angles are. That's from here, 3 pi over 2 to 7 pi over 4. R is negative, so you're looking at the negative r axis from 0 to negative 5. And then back to 0. So from negative 5 and then back to 0. All right, let's watch GC do it. Pretty. Okay, there we go. Got to put it in. See if this is what we did, right? So watch that point. Out to 5 when you reach pi over 4, back to 0. Then here we're going from pi over 2 to 3 pi over 4. We're going from 0 to negative 5. Then to pi, we go back from negative 5 to 0. Pi to 5 pi over 4, from 0 to positive 5. Back to 0 to 3 pi over 2. There it is.